I'm sorry, I should speak in English. This is the third mini course of the school. So I will be talking about rational curves on algebraic varieties. So I should say that this mini course is going to focus on geometric aspects of rational curves. And then next week, Emmanuel Père will give us a mini course relating rational curves with arithmetic aspects of algebraic varieties. So let me just make a brief plan of the mini course. So first, I will start today with some introduction, motivation for the study of rational curves on algebraic varieties. And then I will introduce some elements of deformation theory, especially of rational curves. So this part, I will do no proofs. I will just state the main ingredients that we need. So let me just give you some references if you are interested in studying this more deeply. So there is an introductory book by De Baghe, Higher Dimensional Algebraic Geometry. That provides a very nice introduction to the subject. And then there is a more technical and complete book by Kollár, which is Rational Curves on Algebraic Varieties. So once we have these ingredients, we will move to the third and most important part of the mini course, which is a proof of Mori's criterion for uniruledness. I will define all this. So this is a very important result, and it's classical by now. So this is from 79. And so I've decided that if I want to prove something in this course, I will prove this result, because I believe that every algebraic geometer should actually see at least once the proof of this result. And then finally, if there is enough time, then I would like to discuss the notion, more modern and very important notion of rationally connected varieties. So this is only if I have time, and I will just explain some aspects of this theory. Okay, so let me start. So today we will start with 1 and then start 2. So introduction. So motivation. So let me start by stating a sort of classical approach in higher dimensional algebraic geometry. So higher dimensional, I should say that this means that dimension is at least 3. This also works for surfaces, but it's very important in the higher dimension. which is the following. So you want to study varieties that have of higher dimension. They are much more complicated, for instance, than curves. So the classical approach is, in order to study the variety X, you study the properties of families of curves on X. And since curves are easier to understand than higher dimensional varieties, then you expect that you have a better chance by doing so. So we investigate the geometry of families of curves on X, especially families that sweep out some dense open subset of X. And now, as the title of the mini courses, the mini course suggests, we will be more interested not in any curve, in any family of curve, but families of rational curves. So let me start by defining what that means. So let me fix some notation. So I will always be, or mostly interested in projective varieties. So let me fix X, the projective variety over a field K. The rational curve on X is just the image of a non-constant morphism F from P1 to X. So I would like to make 2 points. So the aim of this introduction is really to justify these 2 points. So point A, if a variety X, so let me say X smooth projective variety, say for the moment over an algebraically closed field. This is not necessary, but for the moment let's fix this. So the first point that I want to make is that if X contains many rational curves, then we are happy. And this is because there is a very well developed theory of rational curves on varieties that allow us to say a lot about the variety X by studying those rational curves. So this is the first point that I want to make. And the second point then is, like, once you agree with this one, then you have to agree with this second one, which is it is important, as we will see, there are algebraic varieties that do not contain any rational curve. So it is important, or it is desirable, to have sufficient conditions that guarantee that X has many rational curves. And actually, I should say that for most of this mini course, we will be dealing with point B here. So for instance, this this third part, Mori's criterion, is exactly a geometric sufficient condition for a variety to contain many rational curves. Okay, so let me start then trying to convince you of point A. So as I said, in the classical approach, it's a very powerful tool to study curves on a given variety. And what I'm telling you is that rational curves are better than other curves. So let me justify this by just stating some special properties of P1 that you in general do not see in other smooth projective curves. So the first very nice property concerns vector bundles on P1. So for instance, if you have a projective variety Ex and you have some vector bundle on X, so you want to say something about this vector bundle. In general, it's very complicated to understand a vector bundle on a projective variety. So sometimes what we do is we study some family of curves on T, and then we restrict this vector bundle to each curve, and this should be easier to understand than the vector bundle on X. Now, this is especially nice if we have rational curves, because of the following result. So this goes back to Birkhoff and Grothendieck. Which says the following. So if E given E a vector bundle on P1, then this is always a sum of line bundles. So then there exists integers A1 up to AR, integers such that the restriction such that E is isomorphic to the direct sum of line bundles of degree AI. And now this is so this is definitely not true for a smooth curve of higher genus. And let me just state a very nice consequence of this splitting. Well, suppose you want to understand whether a given vector bundle is globally generated. So if you are over P1, then E is globally generated. Well, if you look at this splitting here, then you see that E is globally generated if and only if all the AIs are greater or equal to 0 for every I. Now, if you think about this a little bit, you see easily that this means that in order to check that E is globally generated, you only have to check that it's generated at one point. So this is equivalent to saying that there exists a point P in P1 such that the evaluation map from H0 P1 E at the point P is surjective. So this is one nice feature of rational curves. And the second point that is also important is the following. So in general, if you have a curve of higher genus, you may want, so you look at, say, F is an embedding or a birational map of C onto its image in X. So if you want to study the deformation theory of this morphism and the genus, if you want to understand the deformation theory of curves in X, and if the genus of C is at least 1, then it's not enough to consider deformations of the morphism. Because you also have to allow the domain curve C to vary in its moduli, which is mg. And so this can be done, and this is done, but this is an extra complication. While if you are in the case of P1, you know that P1 is rigid under smooth deformation. So in a sense, if we consider morphisms from P1 to X, then we cannot just consider deformation of this morphism. Of course, here we have just to be a little bit careful because we have P1 has a bunch of automorphisms, so would like to mod out by this automorphism. If you really want to study refined moduli space for rational curves, but this is to come. Okay, so this is to illustrate point A, and now in order to illustrate point B, so this is point A. Now to illustrate point B, I would like to point out that not every even smooth projective variety has a rational curve. And even those that have a rational curve, and they don't have many rational curves. So many have very few rational curves. So let me just give you some very easy examples. So the first example, it's actually still not in higher dimension, but already for curves. So 1. So let's see be a smooth projective curve of genus at least 1. Well, then we know that the canonical sheaf of C is actually has global section. So this is not zero. This is not 0. So if we have a morphism F from P1 to C, then what we can do is the following. We can take a non-zero differential form omega, and then we can pull back this differential form to P1. So what that is then a global differential 1 form on P1 Now, this is the canonical sheaf of P1 is O minus 2, so we know that this has no global sections. So this shows that this pullback must be identically 0. Now we have a non-zero one form, and when we pull back by a morphism from P1, and we get a form that is identically 0. So if the characteristic of K is 0, then this implies that F is constant. When you are in positive characteristic, then you have to be a little bit careful, because this morphism may not be separated, and then you cannot conclude this directly, but it is still okay. You just have to notice that this morphism will factor through something totally inseparable and something separable. So you just have to work a little bit, but in any case, you are able to conclude that F is constant. Now, we have a very similar example, but in higher dimensions. So let A be an abelian variety. Then again, we know that the space of global one forms on A is globally generated. So if you have a morphism F from P1 to A, again, you have to choose here a one form that does not vanish identically on the image of P1, and then you pull back this form, you get a 0 form, and again, this will show that F is a constant map. So abelian varieties is another class of projective varieties that do not contain any rational curve. And then you can play with these examples. You can take products of 1 and 2, and then you get a lot of examples of varieties that do not contain any rational curve. Well, some varieties, they do contain rational curve, but only very few. So let me give a fourth example. So we start with A, say an abelian surface. So we already know that it contains no rational curve. And then we choose a point in A, and we consider the blow-up of A at B. So now this variety contains a rational curve, which is the exceptional divisor for this blow-up. So this is isomorphic to P1, but this is the only rational curve on A, on X. So here you may study rational curves on X, but this is not going to be a very interesting theory, and it's not going to tell you much about X. So in order for the theory of rational curves to be actually useful, we would like our varieties X to be covered by rational curve, to have many rational curves. So now let me give you a definition. let X be a smooth. Well, actually, I don't need a smoothness here. Be a projective variety over K, let's say, an algebraically closed field. So we say that X is uniruled. So here what we want to say is that we have a family of rational curves that sweep out some dense open subset of X. So the way that I will state this is the following. If there exists a variety Y of dimension equals to dimension of X minus 1, and a dominant rational map from Y cross P1 to X. So before I give you some examples, let me make a few remarks. So the first remark is that when you learn a new notion in algebraic geometry, you may be to check whether this notion is interesting. You start to see how well behaved it is. So for instance, in this case, we see that uniruledness is a birational invariant. And this is certainly a very nice property of such notion. So, and second, actually, so what this means, if we have a uniruled variety, then you see that for a general point of X, and actually you can even see it for any point of X, there is a rational curve. And conversely, if the field K is uncountable, then we see that X is uniruled if and only if there exists a rational curve through every point of X. Maybe by the end of this lecture this will be clear. So the point here is that if the field K is uncountable, then it could happen that for every curve you have a rational curve passing through it, but you cannot find a family of curves. As far as I know, there's no such example, but in principle there could be. Okay, so now going back to point B, it is desirable to have a sufficient criterion for uniruledness. And this is what we are going to be discussing now. So let me just state a very important theorem. in a sense, this theorem, so this is a theorem of Mori. So in a sense, its proof illustrates very well the points A and B that I want to make. So let's start with X be a smooth projective variety over an algebraically closed field K. Okay, so if we go back to our examples here where we don't have any rational curves, you see that the space of differential forms has some strong non-negativity property. So in this case, it's globally generated. So what about if we ask for the converse? So we have the dual. So let me introduce some notation here. So whenever I have X a smooth projective variety, so we have the sheaf of one forms on X, and then we have its dual, which is the tangent bundle of X, and then we will also be considering its determinant, which is the sheaf of n forms on a variety of dimension n. So this is the canonical sheaf, and then I will denote by kx any divisor on X such that omega X is isomorphic to the line bundle associated to K. So this is just a notation. So as we saw, if this has, as the example suggests, if this is tend to be non-negative, then we have a sort of obstruction for the existence of rational curves on X. So what happens if we ask for the opposite? So if, for instance, we can ask that the tangent bundle is ample. Well, but then it turns out that this is too strong, so what Mori proves is that if the tangent bundle is ample, then X is isomorphic to a projective space. So we have maybe asked too much. But what I want to point out is I would divide the proof of Mori's theorem in two parts, in two steps. So in the first step, and this is what we are going to be doing here. So we notice that the tangent bundle being ample implies that minus the canonical bundle, which is its determinant, is ample. And then there is this very nice part of the Mori's proof, which is to prove that minus kx ample implies that X is uniruled. So in a sense, this gives us point B. This is a geometric criterion asking that the anticanonical class is ample that guarantees uniruledness, the existence of many rational curves. And then there is actually the second step, which is once you know that your variety is uniruled, then you can recover Pn by studying the restriction of the tangent bundle to a suitable family of of rational curves. On X. So this would be point A. So unfortunately, we will not have time to say anything about this point A, meaning how do you use the rational curves to recover information about X. On the contrary, we will concentrate on this first step. How do you prove that a given projective variety contains many rational curves? Now this condition, the anticanonical class being ample, turns out to be a very important condition, and varieties satisfying this have a special name, so let me define them. So a smooth projective variety X is called Fano if its anticanonical class is ample. And the main theorem, the main goal of this mini course is actually to prove that first step, that Fano manifolds are uniruled. So let me restate this. So we will prove X Fano imply X uniruled. Okay, so now for that we will need quite some deformation theory, but before we do so, let me just work out some concrete examples. Very easy examples, in fact, the easiest ones. So of course, the first example of uniruled variety is Pn. So in this case, we have a very well understood space that parameterizes rational curves on Pn in the sense of the minimal degree one. So these are the lines in Pn. So the lines on Pn are parameterized by a variety which is, we all know, the Grassmannian. And inside the Grassmannian, so this is also called the Fano variety of lines on Pn. And inside of this Fano variety of lines in Pn, we have a subfamily X, well, X is a point of Pn. So this is the subvariety of the Grassmannian parameterizing lines through X. And it's easy to see that this is parameterized by Pn minus 1. So we fix a point X in Pn, and then the tangent directions to X are parameterized by Pn minus 1. And then for each tangent direction, we have exactly one line. So I will need this for some computation. So let me make this, this isomorphism clear, explicit. So given a point A with coordinates A1 up to AN, so let me, for simplicity, let me assume, for instance, that this point is the point 1, 0, 0, 0. So given a point in Pn minus 1A, I will associate to it the line parameterized LA, which is, we can parameterize this way. So this is the set of points T, A1S, ANS, ST, P1. As we see, we just have a lots of lines through a given point. And this isomorphism will be needed later on. Okay, so this Pn, actually, you even have you have much more rational curves. You can find rational curves of any given degree. But for the moment, we will be interested in lines. And let me move to the next example, which is the next simplest example of a projective variety is a hypersurface on Pn. So let me denote by X in Pn a smooth hypersurface of degree D. Okay, so we know that the canonical sheaf of X, so this is just by adjunction, we know that the canonical sheaf of X is isomorphic to the restriction of O minus n minus 1 plus D to X. So what we see is that we actually have a trichotomy here. So if the degree D is greater than n plus 1, then Kx is ample. If the degree is exactly n plus 1, then the canonical bundle is linear equivalent to 0. And if the D is small, D is less than n plus 1, then the anticanonical is ample. So by Mori's result, we know that in this case, these hypersurfaces are uniruled. So there is a sort of philosophy here for hypersurfaces that the lower the degree, the closer the hypersurface is to a projective space. Now, for instance, well, if D equals 1, then X is just Pn minus 1. If D equals to 2, then X, so this is a hyperquadric, and then we can do a stereographic projection to show that X is birational to Pn minus 1. And in fact, there are ways we will see that the low degree hypersurface contain lots of rational curves. So let's just do this computation. So let's fix. So we can, let me call Gx. So we fix X inside our hypersurface. So let me make the question first to make it clear where we want to get. So the question is, for which values of D, xd contains lines through every point. Okay, and this can be answered really by computation. So let's fix. So we fix x, a general point, well, any point of xd. well, it's any point, but we may assume that x is this fixed point of Pn, just by making some linear transformation. So we assume that this is this is the point x, that we assume it belongs to xd. Say xd is given by is the zero locus of a homogeneous polynomial of degree d. And then we define a subvariety of the Fano variety of lines in Pn, parametrizing lines through x contained in x. So this is a subvariety of the variety, Fano variety of lines in Pn, which is isomorphic to Pn minus 1. So we want to find the equations that define G sub x inside Pn minus 1. So let's use this parametrization. So we have La in Fx, and La is contained in xd if and only if the following holds. Well, what we have to do here, we have a parametrization for the line. We just have to plug it in the defining equation of the hypersurface. And we have to check whether this is identically zero as a polynomial in T and S. And then if you write this down, so what is that? So this will be a sum of from I equals to 0 to n of, say, G. I think I want this n minus I a T I S n minus I, where the GI in K A1 up to AN is homogeneous of degree I. And notice that the fact that the point belongs to the hypersurface tells us that G naught is 0. So what we see is that, so the conclusion is that G sub x is defined by exactly D equations inside the F sub x, inside Pn minus 1. So therefore, the dimension of G sub x will be greater or equal than n minus 1 minus D. So the conclusion is that if D is greater, or if D is smaller than n, then G sub x is non-empty, and we find a line on through any point of x. This bound here is almost what we would like. So this is what Mori's theorem tells us, that as long as D is less or equal than n, then we find rational curves through every point. But it's okay, because these rational curves may not be lines. So if D is exactly n, then we must look for rational curves of higher degree. but it's possible to find them. Let me just give, for instance, an example. If I take n equals d equals 3, so this is a cubic surface. So we have a cubic surface in P3. So we know that this cubic surface contains exactly lines. So in this case, through a general point, there will not be a line. But then this is what you can do. If you can fix one point. So here is x3 and p3. So we know that there are 27 lines. So let me fix one line L containing x3. Now if you give me any point x not containing the line, I can look at the plane that is spanned by x and L. So this is a true plane in P3. And the intersection of this true plane with the surface x3 will have to be a curve of degree 3. Now this is a curve of degree 3, but it already contains a line which does not contain the point x. So what we see is that this intersection must be a line L union conic, and this conic must contain the point x. So we see that for cubic surfaces it's easy to find the conics through every point, and one can go on and do other constructions for higher dimensional hypersurfaces, but we are not going to do this. So we will prove Mori theorem, so we don't have to go further than this. Okay, so let me just make I think it's at this point I would like to make a remark. Just for completion, I should say that a lot is known about lines on hypersurfaces. So let me just state a theorem that we will not prove, we will also not need. So remark. So here we have to assume the characteristic of the base field is 0. And let x, xt, be a general, smooth, well, once I ask for general, I don't have to put smooth, but okay, general hypersurface of degree D. Then the existence of lines is governed by the degree of the hypersurface. So X will contain infinitely many lines if and only if D is less than 2n minus 3. S will contain finitely many lines if D is exactly 2n minus 3. And then X contains no lines when the degree is higher. So let me just remark that these assumptions that the characteristic 0 and that the hypersurface is general is actually necessary for the statement to be true. There are counterexamples in positive characteristic, and if you don't require the hypersurface to be general, it's very easy to force the a special hypersurface to contain, say, a linear subspace. Okay, so let me just say, so this is we are seeing that hypersurfaces of low degree are uniruled, but we will see, hopefully today, maybe tomorrow, that if D is greater than n, greater or equal than n minus 1, and the characteristic of the base field is 0, then XD is not uniruled. So here I'm assuming that XD is a smooth hypersurface of degree D. So we will see this later on. But let me just remark that there are counterexamples in positive characteristic. So this is not true if the characteristic of the base field is positive. So let me give you a counterexample. So this is the hypersurface in P3 defined by the Fermat hypersurface in P3 in characteristic 3. And I will leave you as an exercise to check that X is uniruled, even though its degree is greater than 3. So this is something definitely special to characteristic 0. Okay, so in fact this will be, so we will see this result, but this is actually a special case of a more general statement, and in order to discuss this I have to introduce some elements of higher dimension algebraic geometry. So let me define the Coderre dimension of a variety. Let X be a, well, for simplicity I will say smooth projective variety over an algebraically closed field K. So we have the canonical class of X. And what we can do is we can look at the sheaf omega x tensored by k for any positive integer k. And then if it has a global section, so if h naught of x omega x to the k is different than 0, then, so this is the same thing as OX K X. Then we can look at the complete linear system Kx, and it defines a rational map phi from X to some big projective space. And we can consider the image of this map and ask what is the dimension. So let me call the K will be the dimension of the image. So this is omega K. So this is the rational map associated to this complete linear system. So if I look at the dimension of phi K, this will be an integer between 0 and the dimension of X. And then what I can do is the following. So first of all, let me define a set of integers associated to X. This will be the positive integers for which we have a global section of this sheaf, for which the H naught of X, omega X to the K, is different than 0. And then finally, I will define the Koderre dimension of X as follows. So this is the Koderre dimension of X. So this is defined to be, well, if that set is non-empty, this gamma X is not empty, then we define this to be the maximum of the decay. And if this set is empty, then we define this to be minus infinity. So this Koderre dimension can be either minus infinity or a non-negative integer less or equal than the dimension of X. And we have already seen some examples. So for instance, for hypersurfaces, so X, XD in Pn, a smooth hypersurface. So we've seen that if D is less than n plus 1, then Kx is ample, minus Kx is ample. Now, if the anticanonical is ample, then this set gamma is necessarily 0. We cannot have an ample divisor whose negative is effective. So this ample implies that the Koderre dimension of X is minus infinity. If the D is exactly n plus 1, then we have seen that the canonical class is trivial, and this says that the Koderre dimension is 0. And if D is greater than n plus 1, then the canonical class is ample, and then of course, as long some multiple of it will be very ample, and so the image of the associated map we have dimension equal to the dimension of X. So we've seen that these values for the Koderre dimension occur. Now for the intermediate values, it's actually easy to construct examples. So for instance, if I take X such that the canonical class is trivial, well, it's enough to take a hypersurface of this type, and if I take Y of Koderre dimension, say, positive, for instance, I can take one of these guys, one of this hypersurface, then I can consider the product, and it's actually not hard to see that the Koderre dimension of the product will be equal to the Koderre dimension of Y. So this way I can produce all the intermediate values for the Koderre dimension. So let me just go back, once we have this definition, let me go back to this statement here. So star is a special case of the following proposition. So here again we have to assume that the characteristic is 0. Then if X is uniruled, we will show that X is uniruled implies that the Koderre dimension of X is negative. So we will prove this. And conversely, we have the following conjecture. So this is one of the most important conjectures in this area, is that, again, in characteristic 0, the converse also holds. Then if the Koderre dimension of X is negative, then X is supposed to be uniruled. Now this is actually would be very nice. So what this, the Koderre dimension is a first rough classification of projective varieties. So this, if you have a smooth projective varieties and you are interested in the birational classification, so the first rough invariant that you define is the Koderre dimension. So this will separate your variety in certain classes. And what this conjecture says is that this class here, corresponding to Koderre dimension negative, are exactly those that are covered by rational curves. So this would be a very nice geometric description of these varieties. But this is an open problem, very important one. Okay, so finally, to finish this introductory part, let me describe or just define one more important class of varieties, which are what we call rationally connected varieties. So the motivation is the following. So let's assume, let Y be a smooth projective variety without rational curves. for instance, you can take an abelian variety. Now, define X to be the product of Y, say, with P1. Now, of course, this product is uniruled, but all the rational curves on X are fibers of the first projection. So here we have the first projection to Y, but all rational curves on X are fibers of pi y. Well, in this case, well, you can study the theory of rational curves on X. Well, it will only tell you something about the fibers of this morphism. So it just tells you that you have a fibration. Of course, this is important, but you don't see much of the geometry of X, because by studying the rational curves, you will not get any information on Y. So in order for the theory of rational curves to be more powerful, it's interesting to have varieties that you have much more rational curves than that. So the problem here is that if you give me 2 points in Y or general points in X, I cannot connect them by a rational curve. So this gives a motivation for the following stronger notion than uniruledness. So this motivates the following stronger notion. So this definition goes back to 92. It was made independently by Campana and Kollár, and Mori. So I will give, there are many different ways to define rationally connectedness. I will give the most naive definition. So for that, let me just put some extra assumptions. So let X be, say, a projective variety over, say, an uncountable algebraically closed field K. And we say that X is rationally connected if for any 2 general points X and Y in X, by general points I just mean points that are outside, that are in some dense open subset of X. So for any 2 points in this open subset, there exists a rational curve connecting X and Y. Again, this is a very important notion in higher dimensional algebraic geometry. Actually took, definition looks very nice, but it actually took quite some time, decades, for the people to come up with the right, meaningful definition. So for the moment, I will just state the definition. And as I said, if I have time in the last lecture, I will in the last lecture, I will discuss this notion a bit bit deeper. Okay, so now we move to the second part. So this is section 2, elements of deformation theory. So we will be interested in studying deformation of rational curves on varieties, and for that we need a parameter space for rational curves. So let me start by stating the theorem. So this is by Grothendieck. That says the following. So I will state it in the most general form. So let Y be a projective variety. And X a quasi-projective variety, both defined over a base field K. Then there exists a space parametrizing morphism from Y to X. Then there exists a K-scheme which I will denote more Y X. Parametrizing morphisms F from Y to X. So maybe this is, let me say a bit more. So there is a K-scheme, I should say locally of finite type. So there is a K-scheme more XY. Actually locally quasi-projective. Parametrizing morphisms F from Y to X. So what does that mean? So that means so there exists a one-to-one correspondence there is a bijection between the K points of this scheme and the set of morphisms from X to Y. And moreover, so there is this K scheme, together with a universal morphism as follows. So we have this scheme morphism from Y to X, and above it we have a universal family for this, and an evaluation morphism to Y, to X, such that the following holds. So what we are saying here is that not only we have a bijection between the K points and the objects that we want to parameterize, but they fit nicely in a family. So for instance, if I, at pointwise, at the level of closed points, the evaluation of the pair F Y is just F of Y. But more than that, actually, the universal properties of this, that's why we call it universal. There is some universal properties for these morphisms. So this space is actually not only parameterizing the morphisms themselves, but it's actually parameterizing families of morphisms. So for any K scheme T and T morphism, say F from T cross Y to T cross X, there exists a unique morphism phi from T to the space of morphisms So here what we have, you can think of this morphism as a family of morphisms from Y to X, parameterized by the scheme T. And what the universal property will say is that this means that T can be seen inside, there's a map from T to this space of morphisms, such that the corresponding morphism is obtained sort of by pullback. So such that this morphism F is given in the following way. So I guess, so this is the identity on T, and on the other side this will be so Y to, so I guess we have to take phi from T to Morse, but then we compose this with F. Okay, so let me see how much time I have. So for those who know what this is, what we are saying here is that we have a certain functor and we have a scheme that parameterizes this functor. So maybe I will just skip the details. If you are interested, you can look for it in any of the references and you will find this in a more precise manner. Okay, so let me just remark that in general, morphisms from Y to X has infinitely, countably many components, many connected components. But each connected component of this space is quasi-projective. So we will not prove the existence of this moduli space, but let me work out just a very simple example. So first, again, let's take x, y to be P1. In the end, this is what we are going to be mostly interested in, and x to be the projective space. So what does it mean to give a morphism from P1 to Pn? Well, that means that I have to choose, so if I call the coordinates st, what I have to choose is n plus 1 homogeneous polynomials of the same degree. So this will be f, say f naught, f n, and these are homogeneous polynomials of the same degree. So in fact, for each degree d, we have a component md of morphisms of degree d. So the space of morphisms from P1 to Pn will be a disjoint union of morphisms of degree d from P1 to Pn. And each one of those will be an open subset of a certain projective space. So here of the same degree, and here we also have to require that they have no common factor. Otherwise we cancel them out. And so what we see that we have to choose n plus 1 polynomials, homogeneous polynomials of degree d in two variables. So for each of those we have a choice of d plus 1 coefficient. So what we see is that this is going to be an open subset because we have to remove those that have a common factor of n plus 1 times d plus 1 minus 1. So for Pn, we see that this scheme is a union of these quasi-projective schemes parametrizing morphisms of fixed degree. Now we can do the same for hypersurfaces of degree d. So example 2, xd, maybe called xe in Pn, smooth hypersurface of degree e. Then again, we have a morphism as before from P1 to Pn, which is given by n plus 1 forms of the same degree, say d. And we have to require we want to require that this morphism has its image entirely contained in this hypersurface. So what we have to do is to plug in this this parametrization into the defining equation, say G equals to 0, and what we see is that, and we will require that this gives a polynomial that is identically 0 in S of T and T. So what we see is that the space of morphisms of degree D from P1 to X, well, this is contained in the space of morphisms of degree D from P1 to Pn, and this is defined by, so if we plug in this equation, so this, each one of these has degree D into this one which has degree E, we get D times E plus 1 equations that must be satisfied. So this is defined by D times E plus 1 equations inside this bigger space. Now this is an open, so this is an open in a projective space of dimension n plus 1 times D plus 1 minus 1. So this in fact may be empty. However, if it is not empty, we have an estimate on the dimension. So if we have a morphism F inside more D of P1 XE, then the dimension of this space at the point F, the point corresponding to F, this will be greater or equal than, oh sorry, here, okay, so this is, maybe I want to write the dimension of X to be n, so let me make some changes here. So we have n plus 1, n plus 1, plus 1, so here we get n plus 2. So this will be n plus 2 times d plus 1 minus 1 minus d e minus 1, and now this is, okay, so this should be, so let me see how I want to write this. So I want to write this as n plus 2 minus e times d plus n. Right. And let me just remark that this number is not any number. You can check that this is exactly the anticanonical degree of the curve. Which is this part here, the anticanonical bundle of XE and the degree of the curve, plus the dimension of X. So we will see, I'm writing it this way because we will see that that estimate in fact always holds, not only for hypersurfaces. Okay. So now, let me describe, I will state a theorem that actually is proved using deformation theory, and then we will use it next time. So this is a local description of the scheme morphism from Y to X. Okay, so before I state the theorem, let me just make an intuitive picture. This is far from being rigorous. Let's say now we are over C. So what we want to describe now is we take a morphism F from Y to X, and we want to describe the tangent space of this space at F. Okay, so here we have our space of morphisms. So above this we have the product Y together with the evaluation map to X. Okay, so I have one point here corresponding to the morphism F. So here above this point I have Y, and I have the map. So I have here, let's say, let me just draw it as a curve. I have Y, and then I have the map F from Y to X. So I have the image here of Y in X. So what does it mean to have an element of this tangent space? So what would be intuitively a tangent vector to this space? Well, you can think of this as follows. So you can take, say the unit disk in C, and you define a map to this space of morphism. So have a little arc through F. So what does an arc here means? So that means that we have a certain family of morphisms Ft for T in this unit disk that varies with T. So we have a morphism, and then we have here the image of Y under these new morphisms. And what happens, so here you look at the limit, so we look at the derivative of this arc at the point F. So if we do the same here, you look at the limit when T goes to 0, what you get is a sort of vector field on the image of Y. So actually what you expect is that such tangent vector will correspond to a global section of the pullback of the tangent bundle of X. So this is, in a sense, complete nonsense. It's not rigorous at all, but it's just to give you an idea of why you expect, of why you should believe that this is, that this could be the tangent space to such space of morphism. So now let me state the correct theorem. And so these are the local descriptions of the space of morphism. So again, let Y be, well, for simplicity, let me say X and Y be smooth projective varieties over an algebraically closed field K. Then the following holds. Actually, I think here we only need that X is smooth, but I think I'll just state it this way. And let me state it a bit more general. So X and Y projective varieties over K with X smooth. And let F be an element in the space of morphisms from Y to X. Then the following holds. So 1, the tangent space at F, the space of morphisms from Y to X, is isomorphic to the space of global sections of the pullback of the tangent bundle of X, as our intuitive picture suggests. Second, this is the tangent space, but that does not mean that, for instance, that this is that every vector here comes from really a deformation of the morphism. So for that, we need to check the H1. So if the H1 of Y F pullback of Tx is 0, then morphisms Y X is smooth at F, and thus the dimension of the tangent space gives us the dimension of the space. It's a smooth of at X, at F of dimension H naught of Y F pullback Tx. Third, so this is the obstruction for say a first order deformation to actually come from a deformation. But in general, what we have is the following. The dimension at F of the space of morphisms from Y to X is greater or equal than H naught Y pullback of Tx minus H1 of Y pullback of Tx. So at least we have an estimate for the dimension of this space of morphisms. And the last local description that we want concerns the evaluation map. So as we saw, this space of parameters comes with a universal morphism to X. And we are interested in describing the tangent of the morphism F. So we fix, so for every Y in Y, the derivative of F at the point F Y is given as follows. So this is going to be go from the tangent space at this product at this point. So the tangent space at F by 1 is isomorphic to H naught Y F pullback Tx. Then we have the tangent space of Y at y, and this should go to the tangent space of f y x. So what it does is the following. So if you start with a global section alpha and a tangent vector at y v, what this derivative does is this alpha can be evaluated at the point y. So this gives us y alpha at y. And then we add the derivative of f at y dot v. So all these properties can be deduced from the universal properties of the space of morphisms when you look at a suitable family of morphisms. So I guess I don't have much time, so let me just make a remark when y is a smooth curve. When y equals c is a smooth curve, then, so if we look at 3, we get the following. So we have the dimension, a lower bound for the dimension at the point f of the space of morphisms from C to X. This is greater or equal. Now on the right hand side, that is nothing but the Euler characteristic of the pullback of the tangent bundle. But now we know what that is by Riemann-Roch. We know that this is the degree of so that this is going to be the degree of the vector bundle plus the rank of the vector bundle times the Euler characteristic of C. And this is the anticanonical class of C times C plus n times 1 minus G. So this is precisely what we had in that example when C was P1. So I guess we stop here today, and then tomorrow we will explore this deformation theory to start the proof of Mori's theory.